Hey everybody. So today's lesson is on average atomic mass. So when you look at the periodic tables and you look at the molar mass below the element, that is actually the average atomic mass. So we get those average atomic masses by taking the average of all the isotopes. So you just don't have carbon 12 in the universe. You also have carbon 13 and carbon 14, and they show up in certain abundances, and we have to check to see which one shows up more to get that average atomic mass. So this one has an atomic mass of 12, this one 13, this one 14. We take the average based on how much they show up in nature, and that gives us our average atomic mass on the periodic table. So let's get into a couple examples. Or let's just get into the formula first. So the formula we use is to get the average atomic mass, we will take percent abundance of isotope 1 times the, let's go with mass number of isotope 1. And then we'll add the percent abundance of isotope 2 times the mass number of isotope 2, and so on and so forth for however many isotopes we have. Some elements have 2 isotopes, some have 5. Okay, I think lead has 5 isotopes, so this is what we're going to be using. So let's say that we have, let's go with, we have carbon 12. So this is our first example. We have carbon 12, and it is 99.45% abundant. And we also have carbon 12, not carbon 12, carbon 14, and it is 0.55% abundant. Okay, let's find the average atomic mass. So we're going to be plugging things into this equation here. We're finding average atomic mass, so we're going to be plugging in percent abundance and mass number. When you plug in percent abundance, you got to make sure it's in decimal form. So we get that by moving the decimal to the left twice. Okay, so for our first isotope, the percent abundance in decimal form is 0.9945. We times it by its mass number, which is 12. Sometimes it's more specific than this. You always use the more specific one. Okay, sometimes I'll give you a rounded one or a specific one. Always use the more specific one if given. We're going to add the percent abundance of the second isotope, which again, we move the decimal to the left twice, and we get 0.0055. And we multiply by the mass number, which is 14. Okay, so we end up with our 2 isotope numbers. We're going to multiply these together and then add them, and you should get an average atomic mass of 12.011 grams per mole. Okay, that's simple as that. Let's do another example. Let's do this is a word problem. Argon has 3 isotopes. Argon 36, argon 38, argon 40. Based on this, or based on the average atomic mass, I'm just abbreviating it, from the periodic table, which isotope do you think is most abundant? Okay, So this is just a conceptual question. There's no math in this one. Let's just look at argon. When I look at argon and I look at its molar mass, it's a noble gas. It's got a molar mass of 39.948. And we have these three isotopes there. Based on the average atomic mass being 39.948, which isotope do you think is the most abundant? Which one affects its average atomic mass most? Well, it's going to be the one closest to its average atomic mass. So the isotope that's probably the most abundant is argon 40. It's the closest to its average atomic mass on the periodic table. Next up, we have something where we could do some math, and then I got a challenge problem for you after this one. Silicon has 3 isotopes. Okay, we have one at 27.97 AMU at 92.23% abundance. We have one at 28.97 AMU at 4.68% abundance. And we have one at 29.97 AMU at 3.09% abundance. Feel free to pause this and do it on your own. I am going to explain this right now. So again, we got 3 isotopes. We're going to do percent abundance times mass number for each isotope and then add them up at the end. So first one, we got percent abundance, which is 0.9223 times its mass number of 27.97. Okay. For the next one, we have a percent abundance of 0.0468 times 28.97. Okay. Plus our last one, which I'm going to put down here because I ran out of room, 29.97. Well, let's do the percent abundance first. 0.0309% abundance times the mass number of 29.97. We do the math on our calculator, and we should get something around 28.08 atomic mass units. Okay. Let's go ahead and let's get our challenge problem. And then we'll be done. All right. So this is one that I feel like they could ask you on the AP exam because it's so difficult. They're not going to ask you an easy one like that. They'll ask you something really tough. Okay. So let's go with lithium. Has an average atomic mass of 6.941 AMU. Lithium has 2 isotopes. Lithium 7 and lithium 6. Okay, so we got average atomic mass and we got 2 isotopes, and I want to know how abundant is each isotope. Feel free to pause it and try this on your own. This is a good little challenge question. This is a good little test your math kind of dealio, okay? But I'm going to go through it right now. So let's just list out what we know, okay? We have the average atomic mass. We have the mass number of the first isotope, which is 7, but we don't have the percent abundance, okay? We have the mass number of the second isotope, but we don't have the percent abundance. Okay, so we got to develop an expression here to kind of help us out. All right, the good thing that we know about percentages is that this should make up 100%, right? So out of these 2 isotopes, when we add them up at the end, one should be 100%. So I got to think of an expression to put in here to help them relate to one another. I only want one variable, right? I only want x. I don't want x and a y. I just want x as my one variable. So since I know that they'll both equal 100%, I could label one of the percentages as x. Okay, so it'll be 7, let's do times x. And then what is my other one going to be? If I know that it's got to equal 100%, and this will be a portion of it, say this was 50%, right? The other one would have to be 100%, which is represented as 1 minus x. Okay, so remember it's out of 100%. So if this was 50%, this would have to be 100 minus 50%. If this was 20%, it'd have to be 100 minus 20%, which is 80%. Okay, so that's the expression we're setting up for the situation. And then what we could do is we could solve for x, and then that'll give us the other isotope in the end. Okay, so let's go ahead and simplify as much as we can. 6.941 equals 7x plus, distribute, 6 times 1 is 6. 6 times minus x is minus 6x. Okay, let's combine like terms. I'm going to minus 6 from both sides, so I'll get 0.941. 7x minus 6x equals x. Okay, so this is nice. All right, that means that x equals 0.941. So my percent abundance for 7 is going to be 0.941, which in percentage form is 94.1% for isotope 7. And for the other one, if we did 1 minus x, we would have gotten 0.059, which equals 5.9% for isotope 6. Okay, so we had to create a little bit of a math expression here, but we were able to solve that average atomic mass problem. Okay, so that's it for average atomic mass. Have a great day, everyone.